What I usually do with this first part here is just kind of remind you guys of what everything means. In a right triangle, you have to have a
right angle.
Correct.
90 degree angle.
Opposite the right angle is always what length of a
Hypotenuse.
the hypotenuse, the longest length. Now, does it matter the other two?
Legs.
No.
There's legs. Okay. Now, what we do is once we place an angle. You guys ever seen that before?
Nope.
No. Theta. It's a theta. It's a theta. Okay. In algebra 2, we are going to use theta as opposed to angle with a degree symbol. I obviously for today and the next couple of days, everything's going to be in degrees, so we don't have to worry about it. But theta is going to be our angle measure. And when you're dealing with right triangle trig, one of the things you have to remember is good old Chief Sokotoa and the Pawnee Indian tribes. So when you're at theta, when you're looking at that other side, what is that side in relationship to theta?
Opposite.
Opposite. So remember, theta always looks at the opposite, and then next to it would be the adjacent. Why isn't the adjacent the hypotenuse? Because it's next to.
It's the hypotenuse.
It's the hypotenuse. Hypotenuse supersedes adjacency. Ooh. Sounded important there. A hypotenuse will supersede the adjacency.
Spell it.
IT.
I said spell it.
Shut. Hey, congrats! I read the paper you took third. Nice for you.
Thanks.
So, Chief Sokotoa. What's it stand for?
Cosine.
Okay. So apparently we remember trig. That's good. It's kind of like it's a circle, but it continues itself through.
Like a guy.
Can you draw a circle with a point?
Yeah, that's a lot of times you see this. That's just kind of the same idea. But if you get fancy, you start, writing things cooler. Yeah, it's like a cursive O. Do you guys remember what the inverse trig functions were?
-1.
The inverse trig functions, the reciprocal properties.
Is that just like
Do you guys remember those?
It's the opposite.
the -1.
It's to the -1 is how you would find the angle, but the inverse, we spent a little bit more time into the inverse trig properties. Bless you. The inverse of sine is cosecant. Cosecant, CSC, cosecant. Cosecant is going to be hypotenuse over adjacent. It's just sine flipped. Okay. The inverse of cosine is secant. And the inverse of tangent.
Wait, the first one should be hypotenuse over opposite.
Oh, sorry about that. And then cotangent's the inverse of the other one. Those are the inverse properties. Those are the reciprocal properties of Sokotoa. The inverse of sine is cosecant. The inverse of the inverse of cosine is secant. And the inverse of tangent is cotangent. We will probably not be finding theta with our inverse properties, but what we tend to do is we will use them in terms of right triangles and things like that to help solve the missing side lengths and all that. One of the things to remember is that cosecant is the inverse of sine. So if you want to write this out, these work going either way. Can I go to a fresh one? Is that okay?
Yeah.
So cosecant is 1 over sine. Or you can say sine is 1 over secant. They can flip back and forth. Because when you're on that diagonal, if you remember, you can just exchange things without it changing anything. Right? And it works for all the other trig properties as well. I can say that secant is 1 over cosine, and cosine is 1 over secant. One of the things, like, people tend to forget that this works. Is that when you have fractions and proportions, let's see, if this is 2/3 and this is 4/6, are those equal to one another? What you can do when you have an equal proportion is you can exchange them along the diagonal and you still get a true proportion. Because is 6 over 3 the same as 4 over 2?
Yes.
Yeah. That's why I can take these cosecant over 1, if you will, and I can change them on the diagonal, and I still get the true statement. Yes, ma'am? Good question. Okay. And then the last one with cotangent, and this comes in a little bit more into play on more of the second half of trigonometry, but I just want you guys to get the idea that where the inverses come from. It's actually one of the things that we are doing right now in pre-calc is we're working with the graphs of the inverse trig functions, the reciprocal property trig functions. So real easy then. Let's go back and see what we remember about your, well, we have that, the specials.
30, 60, 90?
30, 60, 90.
Well, can you do the other 30, 60, 90?
Oh yeah, you're right. That does look like a little bit better, doesn't it? Okay. 45, 45, 90 triangle is what specific type of right triangle? It's isosceles, very good. It's an isosceles right triangle, which gives you congruent side lengths and congruent base angles.
Yes.
I know for a fact that you guys set things up with, if you were with Seb, you'd use the P's and Q's. Okay. The way that I did it in my geometry class was just a little bit differently. I set it up in terms of x's. Some constant times the square root of 2.
2.
Okay. Same thing with the 30, 60, 90. 30, 60, 90, I set it up with some constant times the square root of 3, and double it.
That's extreme.
Yeah. The 30, 60, 90 triangle, if you remember, came from the equilateral triangle. The equilateral triangle were all 60-degree angles. You bisected one of them, you got yourself the 30. They drew in the altitude of that triangle, which gave you, if you did it with 2's for your side lengths, you had a 2, half of it was 1. Used Pythagorean theorem, you got root 3 for your height. That's how we developed all these. This thing came from a square, we cut it on the angle. 1 squared plus 1 squared, square root, we got the square root of 2. Works every time. So the patterns that we start to look at, is up a little bit here, is that we have 45. Opposite the 45 is going to be some value, x. And the reason that I draw it with these arrows is because that's what the angle is looking at. What's opposite you? Well, that's some value x. I don't know what it is, but that's how I can solve it. So if you're given side lengths across from yourself, you can just set up a one-step equation and then simplify it out. Depending upon what we're going to be doing or how crazy we set these with the 45s, there aren't as many of them in this first unit as far as right triangles and solving them like you had back in geometry. These are going to come into play in pretty quick order, where we're going to say that from the 45, 45, and the 90, we're just going to say it's 1, 1, and root 2. Because when we draw it out, it's easier. That's how we're going to be able to write out all of our trig functions via the right triangle with side lengths of 1. Okay. We kind of do the same idea with the 30, 60, 90 as well. When we do this, we're going to say 1, this becomes a 2, and this is, it's the same values less the x's. It's just using the coefficients. Because all of trigonometry is based off of those side lengths. Everything that we do is based off those side lengths, those 1s and root 3s and stuff. So. That algebra for this one then. So that way, if you're given opposite a certain side, you can set up a one-step algebra equation to solve for the missing side length. Okay. And I know you guys did that last year, so it should come. One thing that you will have to do from time to time is simplify your radicals. You guys remember how to do that? How I showed you the trick for doing that in this calculator? You had to take a radical. If you go to your table, you do your y equals divide by x squared. You're just looking for the ones that have the. You have to take the square root of 12. You take 12 divided by x squared. Julie? Go to your y equals table and do like 12 divided by x squared, and just look at your table. As you, oops. If I'm looking at my table, see how I have 1 and 12, 2 and 3, and then it goes all fractions? I'm looking for the last value integers in both columns. That would be my 2 root 3. And it'll also work later on when you do cubics. If you have to take the simplified cube root, you divide it out by x cubed and so on. Right. Excuse me. Yes, sir. Thank you. So real quick. Let's find the sine, the cosine, the tangent, the cosecant, the secant, and the cotangent of our specials.
Should we make this?
That's not a bad idea. I mean, you don't have to do it in this format. If you just want to write them out, it's just as easy. So, like I said, show you guys how this is going to work via just 1, 2s and root 3s and 1, 1s and root 2s. Okay? So if I want to find the sine of an angle, sine of theta, if theta is 30 degrees, that means it's my opposite over hypotenuse. You guys remember that? So what's opposite your 30? What's your hypotenuse? So it's going to be opposite over hypotenuse. It's 1 over 2. So that means the sine of 30 degrees is 1/2. Okay. Now, I want to go right to the reciprocal. Cosecant would be hypotenuse over opposite. 2 over 1. Okay. To the cosine. Cosine of 30 is going to be your adjacent over hypotenuse. Well, if I'm at 30, what's my adjacent? Root 3. What's my hypotenuse? 2. So it's root 3 over 2. Secant is going to be the hypotenuse over the adjacent. And whenever you have that radical in yeah. You guys remember that? Whenever you had a radical in the denominator, you just multiply top and bottom by that radical to rationalize it. So you'd get 2 root 3 over 3. And then tangent. Tangent of 30 degrees would be opposite over adjacent. So it's 1 over root 3, which is root 3 over 3. Cotangent's just the inverse of it. You just flip the fraction. If I flip that fraction, what do you get?
The first one or the actual answer?
You know which one do you think would be easier to flip?
First.
Then do it. Because this is a simplified version of this, but it doesn't say that I can't just flip this one first because it's easier. Because if you think about it, your cotangents can be adjacent, opposite. It's right as root 3 over 1.
Did you just say root 3?
Yeah, you say root 3. Oh, sorry. Yeah, adjacent. Let's try again with 60. I'm not going to write out the opposite hypotenuse for these guys. I know you guys know that. Let's just go right to the fractions. 60 degrees sine. What over what?
Opposite over.
So now I'm at the 60, so I'm going to be root 3 over 2. Which means that the cosecant would be,
2.
very good. Cosine is 1/2, very good. Which means the secant is
2.
and then, bless you, your tangent will be root 3 over 1. Which makes your cotangent root 3 over 3. Flip it. Okay. Now, eventually, these are going to become ordered pairs throughout our unit circle. Because the units.
Is it the thing where it's like a bunch of, it's a diagonal?
Yeah. What the unit circle is built off of is 3 angles. 30, 60, 45, and 60. Right. You get ordered pairs on endpoints. X, Y, X, Y. The way that it works out with ordered pairs via these angles is that if you think about placing this as a right triangle, this is my opposite, this is my adjacent, this is my hypotenuse. My hypotenuse in a unit circle doesn't change. It's always 1. So, or we just, I'll show you what happens. To get an x coordinate here, that's the horizontal distance, correct? So according to this, horizontal distance would be adjacent and my hypotenuse. What trig function is adjacent to hypotenuse? Cosine. So my cosine is my x value. My vertical component would be my sine value. So each of these ordered pairs are developed off of the cosine of the angle, sine of the angle. So the cosine at 30, root 3 over 2. Sine of 30 is 1/2. And these ordered pairs replicate themselves all throughout, because the only thing that changes when you're switching quadrants, if you recall, yeah, your signs, your SIGN changes. Positive or negative, positive, negative, negative, positive, negative for the different quadrants, which means your cosine and your sine values change signs, SIGN, as they rotate. And it's all built out of this. I don't know, it's Pretty cool. Okay. The easy one, 45s. What's the sine of 45? Root 2 over 2. Convenient, what's the cosine?
2/2.
What's the tangent? What's the cotangent? Cotangent. I just said it out of order to see if you guys were paying attention. It's going to be 1. So now if you look at the cosecant and the secant of a 45-degree angle, they're also going to be the same. It's going to be hypotenuse over opposite, hypotenuse over adjacent. They're both going to equal root 2. Because think about here, if I want to find my cosecant, that's going to be my hypotenuse over opposite. If I want to find the secant, it's hypotenuse over adjacent. So they both wind up at root 2s. The inverse trig functions aren't replicated into the unit circle itself, but we still can use them. We can still use them to help simplify things out. Vaguely remember setting these things up, aside from those 3,
Yeah.
then you're ahead of it then. Real fast.
First time
What's that?
I was quoting Frozen.
30, 60, 90 triangle, you're given opposite the 90. What's opposite the 60? It's 5 root 3. Remember, here's what's going on.
Oh, yeah, that's nice.
You know opposite which one? Solve it for x. So that means this 5 value goes here and there. So it means opposite here is 5, opposite here is 5 root 3.
Okay.
And that's what we did all last year. You guys, in Seb's class, you might have done just a little bit differently with the P's and Q's and all that kind of stuff. Okay, Mr. G did it. I think Mr. G does it kind of the way I do. Doesn't he with the X's, I think? Okay. Oh no, you have to press buttons on a calculator. Do you remember how to do so?
No.
All right, well, let's also make sure you guys remember how to set up and make sure that you're in degree mode, okay?
How do you put it in?
In order to put something in degree mode, you hit the button on your calculator that says mode. Convenient that you need to change the mode into degree mode, so you have to press the button that says mode. Bless you.
I have a question. Where's the motor?
Mode button is up in the middle top
That's the
area,
second button.
I got it.
right next to the second. Make sure that it is highlighted degree. Like I said, a lot of these things will default directly to radians. We don't need to worry about radians, as rad as they are.
We're dying laughing.
Hey, pretty soon you guys are gonna get to see the movie. I didn't show you Rad yet, have I? Sweet.
I
You guys
watched
should love it.
I think I've seen it.
Oh yeah, we're gonna watch a little bit of it.
Did we watch it last year? I feel like we
BMX bike one? Probably. It's so awesome we're gonna watch it again.
did. No?
We're gonna watch the music video this time, Send Me an Angel.
Oh.
So if it says solve the right triangle, that means you have to have 3 angles and 3 sides. So they're giving you one of the angles and one of the sides. How, well, this is implied when you have the capital and, I don't know, a degree symbol. I'm going to go out on a limb on this one. What's angle B? 70. So I know that angle B has to be 70. I still got to find side B, and I have to find side C. Now, if I'm going to, and this is where I'm really going to nag you guys about. Reutilize the information that you're given each and every time instead of solving for a piece and reusing that. Granted, there will be times you'll need to do that, but if you don't need to, Don't do it. Because what happens if you set up a problem and you get that first step wrong and you reuse that later on? That's wrong. But if you reuse your givens and use a different trig function, you still have, they're both independent events of one another. You have the probability, a greater probability of getting that one right. So if I need to use my angle A, my 12 is my opposite, what is C in relationship here? It's the hypotenuse, and then B is the, so to find the hypotenuse using trig, what trig function? Sine. So to find the hypotenuse, I'm going to take the sine of 20. It's going to be 12 over C. I'll just use the letters they give us. And if I want to find my adjacent using a different trig function, given my opposite and that angle, which one am I going to use? Tangent. Very good. Little trick. Once again here. Do you remember how to solve when the variable was in the denominator? What was the trick that you did? Just switch them. Switch them on the diagonal. Whenever you have trig functions and you have trig of some angle value equals some number over unknown, you just switch them. And that's the reason was because, remember I had those proportions up there? You can exchange proportions along the diagonal and they don't change. Same deal here. I'd like you guys, when you have a trig function like this, to get in the habit of rounding to 2 decimal places. And that gives you your side lengths. And one thing you could always do to make sure that you're not a complete doofus is that you can always double check it, make sure that the smallest angle has the shortest side across from it. Medium, medium, large to large. Remember that property? I hope. We will do some proofs, yes. We do trigonometric proofs. So I'm getting for my B value, I'm getting B is about 32.97.
Yeah.
And the other one I'm getting 35.09. You guys agree?
Yes.
So when it says solve the right triangle, that means you have to find all the missing parts. Remember how to solve for missing angle? Remember how to do that on the calculator?
Inverse?
Yeah. So let's say that you, try to, do I have an angle like that? I don't know if we do that yet or not. Well, let's just say this. If I needed to figure out my angle measure, if I needed to find my angle measure here, oops, I should probably tell you that this is a right triangle. Helpful. If I needed to find my angle measure here, I know that I have that angle, and I have 2 side lengths. In relationship to that angle, what are the 2 side lengths?
Adjacent.
Adjacent and hypotenuse. Good. So this is an adjacent. That's my hypotenuse. What trig function is adjacent and hypotenuse? Cosine. So that means that the cosine of some angle is 15 over 33. Now, this is where you have to use an inverse. An inverse undoes something. If I take the cosine inverse of a cosine, they undo one another. It's kind of like the inverse of multiplying is dividing. The inverse of squaring is square rooting, and so on. But what you do to one side, you have to do to the other. So you're going to get theta would equal the inverse cosine. Remember that button? Of your angle, of your sides. So 62.96. Just see if you guys remember how to do that. Okay. Remember this?
Oh.
Yeah.
I like that.
That's my helicopter drawing?
Because that was
Yeah. 62.96.
that
Great mistake. Hey guys, when you're doing these things, I know It's all in the calculator. Everything is in the calculator. But please write down what you're going to put into your calculator before you put it into your calculator, because that way I know whether or not you know what you're doing. I can sit here all day and go like this. It's 1. But if I didn't know that the tangent of 45 was or something, it won't work. So I need to know what I'm typing. Angles of elevation, angles of depression. Think of it this way. Line of sight, looking up, or line of sight, looking down. What comes into play here is the ground. Your line of sight, if I'm looking across to the whiteboard here, my line of sight is parallel to the floor. If I'm looking up to the corner, my line of sight is looking up to that corner over there. But if I'm looking straight across, it's parallel to the ground. So it's from here up that I'm looking. Does that make a little bit of sense? So that's your line of sight up is your angle of elevation. That was awesome. So this, it is the little things in life, So you get this line of sight looking up. You guys did that clinometer thing with Seb last year, right? We went down to the auditorium, you guys listened to the protractors. So you did this, and you had to compensate sometimes for this extra height for the eyesight when you measure stuff. It's basically the same thing. They throw a couple of these line of sight style problems in this first section. Basically, it's all of chapter 7 thrown into one section from your geometry book. It's fun. Angle of depression is line of sight looking down. It's still parallel to the ground. You get angle of depression, angle of elevation. They are congruent to one another because of two parallel lines cut by a transversal. You get alternate interior angles that are
congruent. I still don't understand why it doesn't mean the same.
What do you mean?
Like, Mr. Gonzalez always yelled at me whenever I said it was the same.
Bless you. Oh, you okay? What's so funny today? Oh, is that what it is?
Tell your story.
Move! No?
Try to think of a crazy one here.
So, this is always my favorite one. Yes, ma'am.
What did the D stand for on the other
Line of sight looking down. Oh, this just means parallel. Sorry. That's my arrows for parallel.
one?
Oh, okay. Alright, we're good. I thought it was a D for like down.
Yeah.
Yeah.
And why would it be on the angle of elevation?
I thought it was like, why is it dark? Like for the bottom,
Dirt.
dirt. That's what I thought.
Sorry. That was my really bad drawing of an arrow to show that they're parallel. Alright. I don't think we need to worry about throwing them. But whatever, it's just fun. Hi. Oh, this is the one I wanted to do. This is too easy.
That's okay. Yeah, that's okay. Have a highlighter?
All right. An occupant in a lighthouse that is 350 feet above sea level
Oh, I needed these.
observes two ships directly offshore. The angles of depression to the two ships are 4 degrees and 6.5 degrees. How far apart are the ships? So we need to kind of draw this, right? This is where my skills come into play. This is great. Because there's a fence line on the top there so kids don't fall off. And then you gotta put a beacon.
But aren't they usually like this? Like at angles, so it's like they don't talk over you. Sturdier base.
And then they're striped.
You missed one.
That color in the stripes.
You're missing the, like, caption.
Whatever. Here's the water.
Mine's like
How tall is the lighthouse?
I don't know, you moved it past there.
350 feet high. There are not one, but 2 ships at sea.
shit.
It's supposed to be degree marks.
Yeah.
Look at my books. I think they're pretty good.
I've got some bad skills with my artisticness. So you have angles of depression. Angle of depression is line of sight looking where? Down. So what we need to do, move this a little bit out of the way. We have this line of sight. Our line of sight is parallel, is that a better arrow?
Yes.
To the seafloor. And it's looking down to the ships. One of them has an angle of depression at 4 degrees, and one has 6.5. Which one's which?
6.5.
The smaller one is the farther one.
The smaller one is the further one. So this will be a 4 degree here. And that means this one is 6.5. Okay. Buongiorno, como se va? Arrivederci.
Is he right?
No. Not even.
Buongiorno, como se va? That's French.
No, it's not.
It's not right. What are you doing?
Uh-huh.
No, it was bonjour. Bonjour. Oh, buongiorno. That's Italian, I think.
Lucho.
I don't know.
Probably not.
Lucho, is that what
It's buongiorno, mangia. Buongiorno. I was close. So yeah, I was on the Italian Alps. Yeah, it's a regional dialect. You guys just don't understand. So you have angles of elevation, or excuse me, depression at 4 degrees and 6.5 degrees, which means you have angles of elevation of 4 degrees and 6.5 degrees. Hey.
Who knew?
They're asking you to figure out how far apart the ships are. Well, in order to be able to do that, you need to find out how far the ship is from the lighthouse. Which trig value is going to allow you to find that? I need to find this one from here to here, and then this one from here to here, knowing the opposite.
No.
I use tangent. I have to use tangent because I got to find the adjacent twice. Does that make sense? So we have the tangent. That's 6.5 is 350 over something. And then the tangent of 4 is 350 over something else. When I get those two values, how do I figure out how far apart they are? Plus you subtract them. Okay, you just subtract them. Now, I know this was a bit of a crash course on reminders and things like that of everything that you forgot from geometry of last year. Well, we'll see how we go through it. We give you the problems that I have. I think this is the ones that I had from that I used last year, but I think they work out nicely. Let me steal your book just to double check. I put up the new tabs on the website for chapters 13 and 14 because we will switch from 13 for a little while, then we'll jump to 14 for like one section, then we'll go back to 13 and do some stuff as well. I found that when we're solving equations and stuff, sometimes it's easier to solve some of the trigonometric equations in 14 prior to doing some of the graphing, because it works out pretty nicely. So you see here, I think this is gonna work out pretty good. Yeah, that's the distance ones, those are good. Cable car one is on there, good. Yeah, these will be straightforward. All right. We'll do this probably today, and we'll do maybe a little bit more of it tomorrow, but I will start law of sines and law of cosines tomorrow. And then on Wednesday, we'll do what's called the ambiguous case for law of sines, which does bleed sometimes into cosines as well. Yes, ma'am?
You're such a bad child.
No excuse.